organizers for inviting me today. I really appreciate it. And as Will said, I'm going to be talking about the challenges and applications of small databases, proteomics data analysis, and particularly parts of it related to the false discovery rate or FDR of it. Or under certain advertisements, I'm going to quote this, the one topic you all love to hate, end quote. Great. Anyways, so I'm going to talk to you why you should care about small databases. I'm going to talk a little bit about kind of current methods that account for small databases. I'm going to talk a little bit about at the end about how our field actually doesn't have a good solution for dealing with small databases and what the future might hold with that. So I should probably start out with why should I care about small databases? You might be asking, I don't use small protein databases. I use a metaproteome. Maybe I use a full proteome of an organism. Why does this matter? Why should I care? I have many, many proteins in my database. And my response to you is that your effective database size might be smaller than you think. And so what do I mean by your effective database size? So what I mean by effective database size is that you're probably only interested in a subset of the proteins in your sample. A subset of the proteins in your sample are only relevant to your biological question being asked. And so in that case, your sample is going to contain some sort of relevant proteins as well as irrelevant proteins. And so why do I make this distinction between this relevant and irrelevant set of proteins is that you have to actually change your database search as well as your FDR estimation procedure to account for the existence of this kind of bifurcation phase. Now, you may be now wondering, well, I care about all the proteins in my sample. There's never anything that I don't care about. And so here's an example of a situation where you might care about one set of proteins and not another. You might only care about phosphorylated peptides, or maybe the unmodified form. There are proteins in a proteome that can't be phosphorylated or won't be. In another common set, maybe you might be only interested in a single protein, or maybe a single pathway. Another example of proteins that are commonly irrelevant, or things that you don't care about, are contaminants. So think of these as trypsin or human keratins. These are things that we all know are introduced into the sample, but very rarely are actually relevant to a biological question at hand. This is maybe you're interested in forensics. This is kind of the application where I'm going to be talking about this talk today. But maybe you're interested in forensics and you're trying to detect a single protein. Let's say ricin. So ricin is a protein toxin. And in terms of forensics, it doesn't really matter what else is in the sample. You just want to know whether this protein is in there or not. All right, and so that brings us to the outline. Today I'm going to talk about two scenarios that involve small databases. One involves the detection of the ricin protein toxin that I just talked about. Another is the detection of snake venom in blood. This is actually a real court case that was involved. I'll talk about a little bit later. Then I'm going to talk a little bit more about these snake venom samples. And finally, I'm going to kind of talk about maybe some ways we can approach small databases in the future. So before I go into all of that, I want to make sure that I go through kind of the process for doing a database search and estimating FDR just to make sure we're all on the same page. So as many of you may know, a standard protocol exists for searching database proteomics data using a database search. So we have experimental spectrum that have been generated by a mass spectrometer, and we're going to search it against a database of peptides. A user-defined base of peptides, we're going to score them, and then we're going to set some score threshold. And for a particular set of peptide spectrum matches, we're going to control the FDR on that. From that, we're going to get a set of peptides, confident PSMs that we are confident exist in the sample, and then a bunch of spectra that aren't there. The false discovery rate of a set of PSMs is estimated using the target decoy competition procedure. As many of you probably know this already, but just to make sure we're once again on the same page, we're going to take an experimental spectrum and search it against two databases. Or maybe one database is a target database. A target database typically contains all the proteins that you reasonably expect to be in the sample. And then the decoy database, which are peptides and proteins that you don't expect to be in the sample. And these are generated by generally shuffling or reversing target peptides. And so what you do is you're going to search the spectrum against the target and decoy database, find the best scoring target and decoy per spectrum, and then you're going to beat them. And by beating them, you're going to get the best scoring PSM per spectrum. And so in this particular case, we have 4 targets that outcompeted their decoys and 1 decoy that outcompeted their target. And I should probably note that these are peptide sequences and these are just some arbitrary scores that decided them. So after we do this target decoy computation step, we're going to get a list of PSMs after here, some of which are targets, some of which are decoys. We're going to set a threshold, say it like a score of 2, and then anything above that, this set of 4 PSMs here, we're going to calculate the false discovery rate on it, which is shown by this equation, number of decoys plus 1 divided by number of targets. And so in this particular case, we have 1 plus 1 divided by 3. So the FDR of this particular first set of PSMs is 66%. And then typically after that, you're going to kind of remove all of these decoy hits and just report the target hits to the user of the database search in FDR. So now you might be wondering, well, that's a common database search. How does this relevant, irrelevant kind of aspect come into play? And so there's a common strategy out there for dealing with irrelevant peptides that pretty much yields an invalid FDR estimate. This is a method that we called search and select at the time when we talked about it. And it's functioning the same as a standard database search, where you take your spectra, search against the database, you score it, you estimate FDR until you get all your confident PSMs. At that point, you're going to actually separate this into 2 separate buckets. One bucket is confident relevant PSMs, and another bucket is confident irrelevant PSMs. So this is an invalid estimate because FDR is a property of the set, and you can't change the set. If you do change the set, then the FDR that was calculated does not apply to these new sets. And so in this particular case, the FDR was estimated on this set here, this confidence set of PSMs. And now you've broken into 2 subsets. And therefore, the FDR calculated on the confidence set cannot be applied to this smaller subset here. So there is a valid variant of this procedure that controls for FDR when dealing with irrelevant peptides. And it's very similar to search and select. This new method is called group FDR. And the basic idea is that you still do the searches, you still have the same database, but prior to FDR control, you're going to remove anything that matches to an irrelevant PSM. And so then you only have relevant PSMs to calculate FDR to get your confident relevant PSMs, as well as your spectra that you reject. So the key difference here is that if you want to do a valid FDR control when you have relevant and irrelevant peptides, you want to filter out PSMs prior to FDR control, not after. So this is a very simple change that you can do to get a valid FDR. So group FDR is all fine and dandy. It has one potential problem in that it suffers from a multiple hypothesis testing burden. And that's because you're doing a lot of searches against scans against irrelevant peptides. And since these peptides you don't really care about, maybe you hit a decoy irrelevant peptide that has a really high score, and that reduces your power. So we created a different variant called subset neighbor search. This is work I did in grad school with my PI, Bill Noble. And this subset neighbor search controls the FDR without a loss of power. And it's exactly the same as group FDR, except the only difference is that instead of a database that contains relevant and irrelevant peptides, you contain neighbor peptides. Otherwise, the process is exactly the same. You have your spectra, do your database search, and you remove irrelevant PSMs prior to FDR control. So just we might be wondering what a neighbor is. So a neighbor is an irrelevant peptide that is similar to a relevant peptide. And so it's just basically if an irrelevant peptide is a neighbor peptide if it follows 2 criteria. One is that their precursor masses are similar, and 2, if their MS2 scans are similar. And so what we have here on the right-hand side is an example of a neighbor peptide along with its relevant peptide. This is from the ricin peptide, a peptide that starts with RIP, and this is a neighbor which comes from a castor plant from GL. And you can see that they have very similar masses, precursor masses, as well as very similar MS2 scans, with about 70% of peaks in common. And so one thing I do want to note is that neighbor peptides can actually can look pretty different from their relevant counterpart. In this particular case, if you look at here, a priori just looking at sequence, I would never expect these 2 peptides to have similar MS2 spectra, but they do. All right, so now that I talked to you a little bit about how current methods are developed to account for these differences in relevant and irrelevant proteins, I'm going to discuss 2 scenarios. I'm going to apply group FDR and subset neighbor search to both detection of rice and detection of snake venom. So the first one is talking about ricin detection. Ricin is a protein toxin that has been previously used for bioterrorism. It's a 64 kilodalton ribosome inactivating protein found in castor seeds. It actually came into popular conscience following the Breaking Bad TV series, where Walter White used it for assassination. And so this is definitely a case if you only care about the detection of ricin. If you're trying to understand whether someone was potentially assassinated by ricin, this is the only thing you care about. You don't really care about if there's weed in the sample or maybe there's human blood in the sample. And you might be wondering, well, this doesn't really happen in real life. Oh, and I should say, I forgot to mention, this is listed as an agent in the Chemical Weapons Convention, and its use could be subject to the biological weapons conventions. These are conventions that have been ratified by countries throughout the world. And so now you're basically saying, well, this is a contrived example. This would never happen. And no, this actually does happen. So I have a New York Times article right here, which is just saying that a woman who tried to mail ricin to President Trump was recently sentenced to jail. Ricin has also been sent into the mail to New York Mayor Michael Bloomberg, as well as President Obama back in previous years. And most famously, in 1978, it was used to assassinate a Bulgarian journalist who was basically stabbed by the end of an umbrella that had a syringe in it, and that was used to assassinate this journalist. And so, so what we did here is just did some reanalysis of some previous existing data, paper shown here on the right, to see if these new approaches can detect ricin in these samples. And so this is these are some castor seed samples that were extracted to look at whether ricin-like proteins can be differentiated from ricin proteins. So there's many cultivars of castor plant throughout the world. So they took 8 different cultivars and did perform 5 different sample preparation methods on them. This ranged from doing a crude C-mash to actually doing protein precipitation. And so this ended up with 54 runs on them. And so what we found is that the overall point I want to talk about is, which is slightly different from what this slide shows, is the overall point is that both subset neighbor search and group FDR are able to detect ricin in these samples. A comparison between these two methods shows that subset neighbor search outperforms group FDR at about 36.5 PSMs at a 1% FDR, shown here. If you're interested in medians, it's at 2.5% increase. But look across all 54 runs, overall the Q values from 0 to 10%, you can see that subset neighbor search is able to outperform a group FDR. But the main point I wanted to mention is that yes, it does actually work here. We're able to use these methods and get detections out of here. So this is awesome. And so now we're going to try it with a second scenario, which is venom detection. And spoiler alert, it does not work here. So this case is actually a really unfortunate case, as well as a really unfortunate kind of paper. It's a bit of a depressing paper to read. So this came about from a 2014 investigation. It's a Royal Mounted Canadian Police investigation. And it involved a toddler 2-year-old who died when it was in care of a family friend who had kept exotic pets, specifically snakes. And so when this happened, basically the police asked a bunch of academics to help understand one of the hypotheses, which is potentially that the caretaker was negligent and allowed the child to be bit by a venomous snake. And so they had asked a bunch of academic institutions around to see if there was any methods that could detect snake venom in either blood or urine. And so this is a lab out in UBC who performed proteomic analysis on the human blood, and the proteomics analysis strongly suggested the presence of snake venom within this toddler's blood. This work and other work was used to obtain a search warrant, and this ultimately led to this arrest and conviction of the suspect. So just to let you know what their data looks like, they have a huge number of runs. They did really deep proteomic analysis. They split it up into kind of 4 different groups. Either you had a immunodepleted sample or a non-depleted sample of blood, and then after you did that, you either did a gel separation or a Versay separation of the sample. And then they did LCMS, and they did peptide detection by max quant. They had 4 sample preparation methods, about 78 runs. That was a combination of many fractionated runs, and they search a database against human proteins, contaminant proteins, snake venom, peptides, and all that stuff. So their results strongly suggested the presence of snake venom peptides in the blood. So out of 15,000 peptides detected in the blood, there's 111 peptides that could be mapped to 100 snake proteins. What we have here is just the peptide sequences of snake venom peptides that are detected in blood that they were able to detect in blood. So a couple examples here. Out of the 15,000, about 80% were human. Another 20% were ambiguous, means they could be found with either snake or human blood proteins, but about 0.74% of them were ambiguously snake. So after reading this paper, there was a couple of concerns I had about the data analysis. And so this is why I wanted to kind of reanalyze it to see if using different approaches, whether we could come across the same conclusion. So I have here a couple listed about a couple of data concerns. These 15,000 peptides were detected in 0.4% FDR. This is an atypical threshold. People usually use 1% or 5%. That itself is not an issue, but they at least reported that they used that thing. But the main concern was that 111 snake venom peptides were invented by a snake, which is about 0.7% of detections. That's pretty close to the 0.4 FDR threshold that we use. So in some potential case, in a worst case scenario, potentially all of these snake venom peptides are going to be kind of incorrect hits. Another thing that was noticed was that they did PSM level FDR. I have previous work that shows that PSM level FDR is actually invalid. It should be using peptide level FDR. And then finally, also use the search and select method, which I talked about previously. They also had an additional threshold beyond the 0.4 FDR threshold that we use, which is fine, but something that makes it a little hard to kind of work together with FDR. And they also combined the data from the 4 sample preparation methods into a single analysis. And this is concerning just because you don't know whether the scores from each of the sample preparation, score distributions from each of the sample preparation methods may or may not be the same. And so one thing I want to kind of emphasize here is that even though I do have these concerns about these data analysis, is that they do not necessarily invalidate the original conclusions. I want to be clear about that. I'm not saying what they did is they have invalid results. Is that they're it's not saying they have invalid results. I should probably stop there. And the way I got convinced that they probably have valid results is they actually did a lot of manual validation. And so this manual validation provides strong evidence for the presence of venom, despite our data analysis concerns. So right here on the left-hand side are 2 peptides that are detected in these runs. One's a human peptide, one's a venom peptide. As you see, we have great coverage of the MS2 peaks. And the only difference between these 2 peptides is this I and V, valine isoleucine difference, which they're able to detect. And so looking at this venom peptide spectrum, it looks great. I'm pretty confident that that's there. We have another example here on the right, where the venom peptide from the blood, as well as standards they got from 2 different species of snake. I don't forget what these 2 species are, but 2 different species of snake. Looking at the spectrum, I would also be pretty confident of the existence here. And you can also see how they look fairly similar to the standards as well. And so kind of going to the goal of this, we're trying to see if using these methods that specifically are developed for a case where we have relevant and irrelevant proteins, can we use these methods to analyze this data to get the same results or not? So here's all the differences that we made. We replaced search and select with FDR, changed some FDR thresholds. We tried using percolator, and we used peptide level FDR instead of PSM level FDR. If you're interested in my statement saying that PSM level FDR is invalid, you take a look at this paper right here. So I guess now to the results. So subset neighbor search fails to detect venom peptides, as well as FDR. Both of these methods fail. What we have here shown on the right is the number of confident peptide detection as a function of FDR for our 4 different sample preparation methods: depleted, non-depleted, or basic reverse phase, or HL. And as you see, we get some detections at around past 6 to 10%. We get about 15 detections for both group FDR and subset neighbor search. I won't know if you don't see all 4 lines. That's because a couple of them are kind of behind each other. So we thought this was not great. So we decided to continue investigating, and so we actually looked at the peptide sequences that were commonly detected. And this is the list of peptides that came out. Looking at this list of peptide sequences, I am not confident about. I don't trust them because these are really rare peptide sequences. This one has five glycines. This has a bajillion glutamates. I think, yeah, glutamines are glutamates. Sorry. And so I wouldn't trust these. And then if you look actually at a mirror spectrum of this particular detection here, of the theoretical experiment, you can clearly see they are not right whatsoever. So this is telling us that basically this method that was designed for this particular use case, which is detection of a subset of proteins in a larger sample, human blood, it's not working. And so we were trying to kind of troubleshoot what was going on. And one of the things we decided we came up with is that percolator failed to train due to the low number of positive examples, specifically the low number of high scoring positive examples. Since percolator is a machine learning method, it requires a training data. And what it does, it splits your data set into 3 separate parts and then trains on each individual part. And so if you don't have a lot of high scoring targets in there, when you split it up, you're not going to have a lot of high scoring in your subsections, and therefore percolator is not going to be able to figure out how to distinguish between high scoring targets as well as decoys. So we also tried running this without percolator. It's even more miserable. Nothing works. And so this is kind of very odd. What is going on here? Why does this method work for one scenario for ricin detection, but not another scenario, the snake venom detection of blood? So we're going to kind of think more about these snake venom blood samples. And basically, as I said, why does our method work for one case but not the other case? It's kind of made me think of this comic right here, which is kind of the existential crisis of, did we do something wrong? Or is there something about the data that we fundamentally don't understand? And so we don't actually have an answer for this yet, but I have a pretty good working hypothesis, I guess. And so the possible, we think what's going on is that there is not enough venom peptides that are truly present in the sample. So the number of venom peptides in the sample that are truly in the sample are pretty small. So we got through this by discarding a bunch of hypotheses. So one is that maybe not the relevant database size isn't large enough. And to understand what that means, if we go back to this FDR equation, which is the number of decoys plus 1 divided by the number of targets. Let's say the number of relevant peptides in your sample is 10. And your database is 10, not your sample, and your database is 10. If you detect all 10 of those peptides, you're going to get the best FDR you can get is 1 divided by 10, or 10%. And so if you have a really tiny small database, the FDR is never going to be great. It's never going to be awesome. And so maybe that's what's going on. And that's not what's going on in this particular case. We actually have 7.6 million venom sequences. Another related but different hypothesis that we also discard is that maybe there's not enough relevant PSMs. To get this denominator here, it's also a function of both database size and a function of spectra to get this PSM. So if maybe there's only 2 spectra that you're looking at, your FDR is never going to work either because there's not enough spectra or enough PSMs to get you a low FDR. And this is just mathematically true. Well, that's also not the case because we also found that we had tens of thousands of target venom PSMs that we got from our runs. So that's kind of left me with this working hypothesis, as I said before, in that the number of venom peptides in the sample is small, extremely small. The number of true venom peptides that are truly in the sample is really small. And so this has brought me to a kind of a frame of mind that I really didn't appreciate until thinking about this more. And so there's actually a gap in our proteomics data analysis kind of workflows that we haven't really dealt with in this field. And this only comes about when you think about this in kind of 2 different angles. How big is your relevant database size, or just how big is your database? And then how many of these peptides are actually in your sample? If your database is large and you have a lot of those peptides in your database, that's a standard database search that is tried and true. It works really well. Subset neighbor search and group FDR was developed for this particular situation, where your relevant database size is fairly small, not minuscule, but fairly small, and those peptides are actually truly in the sample, a fair number of them in the sample. However, what we don't have as a field is this side, when the number of relevant peptides in the sample is really small. Truly in the sample is really small. No matter if the database size is large or small, we have a gap for here. And so what we need actually is the field needs new confidence measures for single or small number of PSMs. And I don't have a solution, but this is something that I noticed that we need as a field. So it's kind of really interesting. And so now I'm going to talk a little bit about how we might want to approach this solution, how to do this in the future. So really the possible path forward for this particular case where the number of peptides that you're truly interested in the sample, only a few of them are truly in the sample. So an alternate slide for this is more probably along the lines of, have you thought of X, Y, or Z? Because some of you audience may be thinking, well, have you tried this? Have you tried that? Have you tried that? And I also say, I haven't tried them, but I've at least thought about them a little bit. So one thing that you can think about are calibrated scores. So calibrated scores provide a value of significance for a single PSM. And what I mean by calibration is not in kind of the mass spectrometry instrument sense, but in the statistical sense. And so a score is calibrated if a score of X assigned to one PSM has the same significance as Y assigned as score of X, sorry, that's a typo, as X assigned to a different spectrum. So a score of 3 has the same meaning no matter what PSM you have. And many scores out there aren't calibrated. Right here we have the score distribution of X scores as a function of precursor plus 3 charge and a precursor plus 2 charge. If you look at here, if you have a score of 1.5, it's a much better score for precursor charge 2 versus a plus 3 charge spectrum. And so with a calibrated score, these distributions all kind of overlap with each other. And so it has the same, a score of 1.5 would be equally significant. A very common example, there's examples out there in the field, which include the MSJ plus E value, exact P value, and combined P value. So these scores exist out there. Problem is what is a good score? We get these P values out of it, and we have to set eventually some arbitrary score threshold, which is not satisfying in a sense. And also, what is considered a good score is going to be kind of dependent on how good the spectra are. You know, how do you compare across this when you have one spectrum that looks really great and maybe one's a crappy spectrum? So that's a little unclear at this time. So going back to the search and select method, which I said was invalid. So I will mention that it is valid under an assumption that the relevant score distribution exactly matches the irrelevant score distribution. And so for certain scenarios, this might be a valid assumption, and for certain scenarios, this might not be a valid assumption. So if you do think this valid assumption, you can totally use this method out here. And this method can boost the performance. And so what we actually did is we actually tried the search and select method on the Venom data set, and we were able to get a bunch of detections out of it. And that's because basically these irrelevant detections kind of boost your confident irrelevance scores over the score threshold because they kind of carry them over. So that's great. But in certain cases, for example, this Venom detection, you can't assume that. And so this doesn't really work for all cases. Another thing that you might want to think about is PEP values, posterior error probabilities. It's almost a great solution as well. For those who don't know, the PEP is a probability that an observed PSM is incorrect. Right here on the right here is a figure talking about the difference between FDR and PEP and how you calculate it. And so the PEP is little b, little a plus little b. So it's this plus divided by the sum of this. Whereas we have the areas over here for FDR. So if you're able to, if you know these distributions and you have a score, you're able to calculate a posterior error probability. That's awesome, and that can exactly gets us to what we want. The main issue with that is that the parameters of this distribution, specifically the parameters of incorrect PSM score distribution and the correct PSM score distribution, are learned from a set of labeled training data. Most commonly, this PEPs are calculated by percolator, and percolator needs this labeled training data to understand what these two score distributions are. And if you don't have a lot of good scoring training data, you're kind of screwed. In this case, with the snake venom, we don't have enough high scoring training data because there's not enough high scoring venom PSMs in our database. And so when you try to do PEPs, this is just the number of the PEP values as a function of our Q value for the detections. You can see they're all really, really bad. It's not good at all. The probability that they're correct is almost 1, so not good at, so basically not possible. Another solution that maybe people might be thinking about would be static models. So static models are used to boost the power in small experiments. And the concept of this is that you can create train a percolator model on a large data set, and you just kind of keep the model weights and use those exact model weights on a small database, on a small data set to boost your power. These static models have been shown to successfully boost the power in runs with few PSMs. What I have here is data from a single cell proteomics analysis, where if you do kind of a dynamic percolator model for single cell data set, you get less power than if you use a static model trained on other single cell proteomics data. So this method works as long as you assume you have an independent training data that is large and similar to your small data set. So this single cell proteomics data, we have a fair amount of that. That's going to work. We have a lot of phosphorylated proteomics data out there. Static models will also work here. But what if you don't have this large training set? Maybe you're interested in a much rarer PTM. Maybe you're just interested in, maybe you're working through proteomics and you're saying, I want to make sure that only this in this particular peptide is modified in a way that no other modification has been seen before. You don't really have that. Once again, in the venom, we don't have many other examples of venom in blood at this time, and so static models don't actually work for a subset of these cases. And finally, maybe we just need to go back to manual validation. This was really common before the advent of database searching, and back in the sequence days, and FDR control. So maybe you just have to look at things by hand. This was going to work fairly well, but there's always these problems of it's not scalable. If you have hundreds and hundreds of PSMs you need to manually validate, it's going to take a lot of time and effort. It's going to be subject to opinion in that I might have a different answer from the person next to me, but it's going to be a good idea for a small number of PSMs. And in the cases where we truly think that the number of relevant proteins in our sample is really, really small, maybe that's the way to go. So that was a whole lot of kind of ideas, thoughts, whatever, but really we still haven't solved this particular problem, which is how do you create confidence measures when we have a small number of PSMs that are relevant and are high scoring or things like that. So once again, new confidence measures for single and small number of PSMs are needed. So that I am done. There's some conclusions. So analyzing proteomics data with small databases requires different methodologies than its traditional standard approaches. So group FDR, subset neighbor search, these are defined methods. New approaches have been developed for these situations. As I said, group FDR and subset neighbor search. What's kind of more interesting to me is that these approaches sometimes work and sometimes fail. And they mostly fail in the case where the number of proteins and peptides that you truly care about, there's only a small enough number of them that are truly in your sample. And because of this, we don't actually have a way to understand how confident we are for these particular detections. And so we actually need new confidence measures for single or small number of PSMs. With that, I'd like to thank everybody who helped me on this. At Bill Noble and Deanna at University of Washington, as well as Uri Kike at the University of Sydney, helped me develop subset neighbor search and helped me learn a lot about FDR. Daniel Lewis at PNNL helped me analyze the snake venom data. I'd like to thank my funding below, and I'll take any questions. Thank you.
Awesome, Andy. Thanks a lot. That was very interesting and thought-provoking. If there are any questions, please put them in the chat or the Q&A functionality. I will start off with a question. As far as I know, most tools just do the very simple way of estimating FDR and like targets over decoys. If you're lucky, it includes a +1 correction, but generally it doesn't it's not any more advanced than that. So my question then is, do we really need to educate the community and overhaul all of the tools to implement these more advanced ways of calculating FDR? Or is this only really for more like niche applications like the forensics use case, etc.? And maybe for like the standard, bulk proteomics, we can, the rough and dirty methods are sufficient.
Yeah, and that's a great fundamental question. So there's a couple things to think about here. So even though there might be niche fields, it's good to actually have methods for niche fields. So, I would say PTMs are not a niche field. Phosphorylation isn't a niche field. And that's actually a case where you actually have these relevant irrelevant split. And we have a lot of phospho data, but we don't have other PTMs out there. I can't name them off the head right now because we only care about phospho in this field, but there's plenty of other modifications out there. And so this is an example of that's not as niche. People really care about PTMs in the field. But I would actually kind of agree that in many cases, this probably doesn't matter too much. Um, there is always this kind of distinction between what is okay enough for kind of users as well as the statistically rigorous thing. And of course, I would love everyone to have statistically rigorous methods and all that stuff. But most people, that's a lot of work for them to do. Another thought is that the people who make tools is a lot smaller than the people who use tools. So I don't think it's probably necessarily that difficult to revamp a lot of different things. Because there's maybe 10 to 20 most database search engines out there that are really, really used. So we really need to just convince 10 to 20, or maybe just even half of them. Because as you said, there may be some people who are just interested in bulk proteomics or just interested in hypothesis generation. So yeah, there's some thoughts about that.
Okay, yeah, that makes sense. And you kind of recommended at the end manual validation, which is a controversial recommendation, I would say, for our target audience. Maybe with like these new fragmentation intensity prediction models or retention time prediction models that can give you more confidence in the PSMs compared to just simply are the peaks there or not, what the traditional search engines did. Do you think
Yeah,
that extra information is sufficient to have enough confidence in the PSMs?
it's a good question, and that's probably another way that's a good idea. I haven't really thought about that, but Prozid, all these kind of predictive libraries, maybe that is enough information to be really confident in. But at the same time, we actually still don't have kind of these theoretical statistical confidence measures. This is all kind of other pieces of information, like okay, their fragmentation looks better, looks similar by stops, a search, and then it has similar retention time. Um, that is unsatisfying in some sense because you will always have to have a arbitrary score threshold for both. How far apart the retention has to be, how far the score has to be before you accept it. And so we don't actually have kind of like these set statistics like FDR for that particular case. And maybe that will help us. Maybe it doesn't. But for the really small cases where FDR doesn't work mathematically, what I would think is that would help you filter down the number of possibilities enough where you only have a 2 to 10 or a very small number that you can manually validate. I think if you go to the really extreme levels, to a point where maybe people start talking about MRM or PRM, then you do manual validation at that point. So yeah.
All right. And with the snake venom court case, what was the verdict there? And did proteomics then whose results might be questionable then, did that play a role in the outcome of the trial?
So this is why I was very clear earlier when I said that my concerns with data analysis did not necessarily invalidate the original conclusion. I was very clear about that. Because why I put that disclaimer up. This is also why I put the slides up about how they doing those as actual manual validation slides. Just and so the guy was convicted. He was in the end, and I should also mention that in the forensics case, there is a lot more evidence that is also kind of generated as well. There's another professor, I believe, out in Colorado who kind of looked at scales as well as potentially bite marks. I can't remember, but I want to be clear that this is one small piece of information in a whole body of evidence, and that even though there might be concerns about data analysis, I'm pretty confident based on the manual validation that we did that there's actually venom sample, zinc venom peptides in there. You know, we could quibble about how many there are in a sample, and that's not something that the justice system, at least how I should really would care about it at this time.
Yeah, and maybe one question compared to the manual validation. There we did see indeed some decently looking spectra that did seem confident peptide spectrum matches, but I don't think I saw those in your percolator reanalyses. There you just had the weird glutamine repeats. So did those spectra get different assignments in your reanalysis, or did they not pass the FDR thresholds?
They didn't pass the FDR threshold.
Okay.
And I think that's because the percolator model just wasn't able to train, and so it just spit out. It created a weird model and spit out weird results.
Right.
Because if you have a machine learning model that isn't able to accurately, separate the two, who knows what's actually going to spit out in the end.
Yeah, that makes sense.